Okay, infrared spectroscopy. Okay. This is the interaction between the photon in infrared region with the molecule. If you look at the graph here, this graph showing the energy and the internuclear distance between two atoms that bonding together. So as you can see from the graph, uh, if the if we have first atom at this position and the second atom at the very end on the right hand, so after you move the atom from this infinite uh, distance closer to the first atom on the very left hand here, the energy level of the system is decreasing down. This is because of the chemical bonding between two electrons from first and the second atom, right? Because normally single electron contains magnetic moment. Then if two atoms coming together, single electron pair up, then the the magnetic potential energy of the electrons is decreasing down by pairing up things together. So energy going down like this. But if you come too close together, then the positive charge or the nucleus of the two atoms having kind of electrostatic repulsion between two nucleus, and the energy raising up again to the this graph. So this is the what we can say that this optimum energy level here, the lowest energy state here, the distance between the two atoms is called bond length. Okay, and the energy between this point and this point is called bond energy. So actually, the bond length is not fixed here at this distance, but normally two atoms that bonding together like this, actually there is only two nucleus of positive charge, and then you have electrons. So there's nothing to fix the distance between the two, right? So two atoms kind of wobble, right? They can squeeze up, they can just going far apart from each other a little bit. So it can be depicted here as they are kind of spring connect two atoms together. So as a spring, they can just wobble, right? Stretch and squeeze, things like that. So as you can see from the graph, the stretching like this, if you have one atom here and the second atom over here, they can stretch out, squeezing down like that. Okay, so it's kind of spring. And this is called vibration. The vibration of atoms is quantized level, similar to the electron excitation of atoms. So as you know, electron can jump from ground state to the excited state from level K to L, M, N, O, P, Q, things like that. Vibration as well. Two atoms vibration, like stretching and squeezing, is not in any frequency, right? But it have to be vibrate in a specific frequency, a specific energy level. It is quantized. So let's say that if this is the ground state of the vibration, right? It's stretch, squeeze, stretch, and squeeze, right? So if you just excite it to the second level, right? So it requires energy, right? And the frequency of stretching is getting higher because of the energy level increasing. And this energy gap is in the IR region. So this is why we can use IR photon in order to excite the vibration of particular chemical bonding. Okay. So if you have different kind of chemical bonding, you need different IR energy to excite it from ground state to the excited state. And actually the vibration mode can be divided into very many types. Okay. First of all, it is called stretching. Right? So you have kind of ground state, right? Stretching and excited state, stretching, things like that. If you have two atoms, let's say, okay, I would say carbon and hydrogen, for example. If they are very close together, the En electronegativity can work very efficient, right? So the polarity of the bond is higher. But if you stretch the bond out a bit, right? So the interaction between two atoms, interaction between two nucleus and and the electron clouds is weaker. So the dipole moment or the polarity of the bond is decreasing, right? So by stretching and squeezing, the polarity is changed, right? So this is the electronic pole, right? The dipole here is electronic pole. You have positive pole and negative pole. Positive pole on hydrogen atom, negative one on your carbon atoms, thing like that. And also for bending, right? There are many modes of bending, like scissoring is like a scissor. Right? You close and shut this scissor, thing like that, and rocking and out of plane bending, thing like that. All this kind of thing can somehow change the dipole moment of your molecules as well. Okay, so by changing the dipole molecules, like stretching, for example, in this picture, if two atoms getting closer by squeeze the system in together, so the dipole moment is getting higher. Then if it's stretched out, the dipole moment is getting smaller, thing like that. So by stretching of the chemical bonding, you're changing the dipole moment of the molecules from very high to low to high to low to high to low, thing like that, right? So if this kind of stretching frequency is related or resonate with the IR, right? Changing of the electronic field of IR. So if it's synchronized, that means the IR can then excite your vibration mode of the chemical bonding to the higher energy state. Okay, so this is how the IR interacts with your compound. So obviously, if your chemical bonding here, if there is no dipole moment, then there is no interaction between the dipole moment with the electronic field of your IR photon. Okay, so this IR can active with only the polar bond, polar chemical bonding, polar covalent bond, sorry. Okay, so if you trying to find the relationships between the vibration and the physical properties of bond, so if you look at atoms, like if we have carbon atom, right, the first bond, this carbon atom connecting with hydrogen atom, and the second bond with oxygen atom. Oxygen is heavier and bigger, right? But hydrogen is smaller and then lighter as well. So let's say if we just hang these two masses on the ceiling, okay, and we just bring these two masses, pull it down in the same distance, and then we just release, let it go. So what happens is they just, with the spring, right, they're bouncing. The bouncing of the lower mass and higher mass, which one is higher frequency? Obviously, it's the lower mass, right? It's the lighter atoms. Right? So this is by the moment of the inertia, right? So as you can see, the chemical bonding between heavier atoms tends to have lower frequency, right? So that means in order to bring it up to the excited state, you need lower frequency of the IR spectrum in order to excite the system up. So it depends on the mass of atom. Not only the mass of atom, it depends on the strength of chemical bonding as well. So the strength of the chemical bonding is like the strength of the spring. Right? So if you have a strong spring, very strong one, and again you pull it down from the ceiling with the same distance with the weaker spring, so the one that have higher frequency of the bouncing is this one, right? So we can say that the triple bond has higher frequency than the double bond and higher frequency than the single bond, respectively. So you can then excite the stretching of the spring by different frequency of the IR as well, right? So higher frequency of IR can then excite the double bond, right? But in order to excite a single bond, you need required lower frequency of the IR spectrum, things like that. So if you have different chemical bonding in the molecules, they absorb different region of the IR. Right? But yeah, anyway, there are just two main factors: mass of atoms and the strength of the bond. Right? So by these two factors, you can relate the region of the chemical bonding in the molecules by IR spectrum. And this is the instrumentation. So firstly, you have IR light source, and then pass it through your sample. The sample holder is very specific because almost every chemical bonding absorbs IR. So you need kind of thing without covalent bond, right, in order to prevent it from the absorption of IR. And then if you have absorption of IR, then it obviously will ruin the spectra of your covalent compound or organic compounds. So we normally use potassium bromide crystal, grow it up into a very huge crystal structure and cut it into kind of glass pieces, right? Actually, it's KBR piece, KBR disc. So from KBR disc, you just drop your sample in between, right? And then after your IR light passed through it, it absorbed some kind of infrared spectra in a specific wavelength that corresponding to the stretching of the excited state of your compounds. And then it go to the detector, and this is what we can see. So on y-axis, it is percentage of the transmittance, and on the x-axis is the kind of factor code wave number. So the wave number is the reciprocal of the wavelength. So by the equation E equal to, oops, sorry. What? So by the equation E equal to hc over lambda, right? Or E equal to h nu. So what we can see is 1 over lambda, or so this is hc nu bar. So nu bar is 1 over lambda, right? And this is called the wave number. So as you can see, wave number is direct proportion to the energy, and also wave number is direct proportion to the frequency. So this is your x-axis. So normally in organic compound, we normally observe the stretching of the system between 600 to 4,000 wave number in reciprocal centimeter unit. Okay, so on the right hand, this is low frequency, low energy, and on the left hand, the energy is higher, frequency is higher. So it tend to have lower mass on the left hand, and also double bond, triple bond on the left hand, single bond on the right hand, and higher mass on the right hand, things like that. You will see the relationship in the IR spectra afterwards. Okay, so this is and another thing, we're just talking about the presence of IR spectra, no? So 600 heavier atom, weaker bond, 4,000 lighter atom, stronger bond, and the percent transmittance on the y-axis depends strongly on two factors. The first of all is the number of bonds. If you have such a bond, right, like if you have ketone, and if you have like dione or trione, you have more than one C double bond O. So it will have higher percent transmittance, right, because you have a higher number of bonding. And also depends on the polarity as well. As I said, that the IR is you playing with the polarity of the bond, right? Because you synchronize the IR, the electronic field of IR wave with your polarity of chemical bonding. So if you have kind of non-polar bond, you have no interaction, and percent transmittance is still at 100%. So if you have very strong, very high polar bonding, even though you have just that one bond in the whole molecules, but it interacts very good with the IR, right? So synchronized very good with the IR. So percent transmittance is dropped down, right? Because it's absorbed the IR effectively. Right? So this is the West number and the percent transmittance. So this is what we normally use in the IR. So what I want to show you first of all is on the left hand around 3000 is CH bond, right? Because hydrogen is very light, okay? So very light atoms vibrate very quick, right? Very fast. So it present in the left hand side region, right? Around 3000 something. It's CH bond, NH bond, OH bond, everything about hydrogen is on the left hand. But then, if you have CC bond, CN bond, CO bond, thing like that, it depends, right? But anyway, it's around here. But anyway, if you have CO bond or CN bond, it depends on the bond strength of CO and CN as well. The triple bond is about here, right? So it's about 2000 something. If you have C triple bond C or C triple bond N is on this area. But double bond, it drops from 2000 to 1600 approximately. So this region is for C double bond C and C double bond O because it's weaker than the triple bond, right? So single bond is around here, less than 1400, the single bond. And because you have CC bond, which is single bond, right? The alkane thing, in almost every organic molecules, right? And you also have like alcohol, amine, and C single bond N, C single bond O. So all of this kind of thing you mix together here, and it's very hard for you to distinguish between each particular chemical bonding. So we call them as fingerprints. And also the vibration is in here in the fingerprints as well, and vibration is very complicated. So all of this thing less than 1400, we normally ignore them, right? So we tend to use the thing around 1600 up to 4000 West number. Right? So if we look closer, normally 1600 around here, 1600, 1700, thing like that, is a double bond area. But as you know, that C double bond C is slightly nonpolar, but C double bond O is very strong polarity, right? So this interact with the electronic field of IR better, right? So the absorption of this C double bond O is stronger than the absorption of C double bond C, right? So the percent transmittance of C double bond O is very dropped down from 100%, right, to very bottom of the graph. Okay, and again for C triple bond C and C triple bond N here, the nitrile and the alkyne as well, similar to this one, right? Because nitrile is higher polar, right, comparing with the alkyne. So alkyne you will have a weak absorption, but nitrile you have strong absorption. Right? You have a very sharp peak downward. Okay, for C triple bond N, and then for C single bond H. C single bond H from the alkane and alkyne. C single bond H of the alkane is sp3 carbon, right? So this chemical bonding is weaker than sp carbon of the alkyne. So because CH here is stronger, then you have higher frequency of vibration appear on the left hand. So we normally use 3000 as the indicator. If you have absorption under lower than 3000, it is the absorption of alkane. But if you have alkene, CH of alkene, CH of the carbon double bond, no? So it's sp2 carbon, it's slightly higher than 3000. But if you have alkyne, C single bond H with the sp hybrid carbon, it appeared around 3300. So that's the alkyne. And But anyway, the alkyne appear at the same region as NH and OH, but the shape of the absorption are different. Because NH and OH, you have kind of hydrogen bonding. So this hydrogen bonding, this oxygen drags your hydrogen atom out a bit. That means OH bond distance is varied by this kind of hydrogen bonding. So what we can see, or what we can observe, is the broad absorption. This is the characteristic absorption of NH and OH, or any kind of thing that can have hydrogen bonding. And the bond strength and bond length can be varied by this kind of interactions. So this is summarize of the IR pattern that you will see in organic compound. So I will show you in the next video.